Hey guys, today the plan is to do round 671 and there's going to be a lot of upcoming stuff. I'm not doing the Accurate Beginner contest today, both because it's early and because it's on the same day as this one. However, I will stream it later, like next Wednesday or something, so don't worry about that. And speaking of streaming and content in general, there's going to be a lot of it. We're going to have a lot of videos coming up this week. You can join my Discord, which is I'll hopefully link in the description if I remember. But you can join my Discord for the exact schedule, but trust me, there's going to be a lot coming up. It's going to be great. Without further ado, we'll update the subscriber count. We broke 1,500, which I'm happy about. It's a nice number. And that will do it, I think. So we should get into the contest. Okay, we have test cases. We have a number n. And this is the Valorant round, right? Okay. Consists of n digits. Digits are numerated from 1 to n. Unmarked digit and market. Odd positions, but not even. Wait, what? The match ends when there's only one unmarked digit left. So is it really just n mod 2? Because if there's an even number of digits, then the even player will win, and otherwise, what? Oh, you have to actually, wait, what? Unmarked digit and market. Oh, it depends on the value itself. Okay. Fine. So basically, odd and even digits are independent. So if a player can so it only depends on the player who actually can make moves. I guess. Struggling to word this. Like say Raze is the person who, say player 1 is the person who's gonna end up with the final like values. If there's any odd digit in the digits that he can remove, then he'll rather do that, and then he'll remove all the even ones first. So first of all, only depends on the player who has control, and then all they need is at least one of their digits to be done. 2 equals targ, can equals 1. So if targ equals 0, then you can print cout 1 plus not can, else cout 1 plus can. There's a bit more bitwise magic you can do here, but I don't really care. It doesn't matter that much as long as this works. And it doesn't work. What? Now I'm confused. I plus 1 mod 2 is equal to targ. Why does that not work then? I plus 1 mod 2 is equal to targ. So targ equals I mod 2 means targ should be 1 in this test case. Targ should be 1 in this test case. What? So what's happening here? Oh wait, this should be switched, I think. Because targ equals 1 means we have the first plan. Come on. If targ is equal to 1, then okay, what now? If targ is equal to 1, then we want to print 1 plus. Yeah. What? What is happening here? Why is this? I plus 1 mod 2 is equal to targ. If AI mod 2 is equal to targ. So is it never thinking we can do it? Ugh. It's messing with my output. So it doesn't think we can do it here. Why? Why would you not? 0, 2. 0, 2. This target should be 1. This can should be 1. God, there's something very stupid happening here. Oh my god. Yeah, that's stupid. We have to actually like use the digits instead of some random numbers that don't exist. Ugh. How did I mess this up? Okay. That looks right. I hope so. God, that took way too long. And it might be wrong anyway. Okay. Alright, that's a great start. Let's high places. Let's get high and decide to craft staircases. Oh boy. Staircase with end stairs is called nice if it may be covered by end disjoint squares made of cells. All squares should fully consist of cells of a staircase. And disjoint squares. Okay. So missing a square is only nice if it's a power of 2 minus 1. So yeah, because say we have like 5, then we can do this, and then it takes 3, but there's like any I think the conjecture here is that any like say you have a number x and you want a staircase with n steps, then round x up to the nearest power of 2, and then subtract that from 1, and then it's going to take that many steps for any x. So only if x is equal to this number can we actually have both n steps and n squares required. So that basically does it. So basically we just literally check all powers of 2 minus 1 and that will work, I think. This should be long so we don't overflow. Okay, am I missing something? Am I still missing something? I guess I must be. Because it says no more than X cells. In total. Wait. Oh, in total? Wait. What? Oh, cells, I guess. Not indent. This is such a weird way to ask that. I don't know why they would do it like this. Okay, so it's specifically that number of cells. The cells is n times n plus 1 over 2, just basic triangular numbers, and essentially it has to be a power of 2 minus 1, so we use that many, and we just go for it, I hope. I don't think it should overflow because we only iterate up to 30, and we just checked it for the maximum possible answer. Okay, that took longer to test than it should have. Alright, whatever. We got more test cases. Okay. COVID 2069. Each account has a rating described by an integer, can possibly be negative or very large. Killjoy's account is already infected and has a rating equal to X. There are n accounts. I see. So you can infect every uninfected account except, wait, is it always? Wait. I'm confused. Oh. Okay. Can Killjoy participate in contests? Oh, no. Okay, so there are three cases. Either everything is initially infected, in which case we already win. So we're going to count the number of infected accounts. C into AI. Come on. If AI is equal to K plus count. So if count is equal to N, then we automatically win. Else if we have at least one account, then if we have at least one account that's rating is equal to Killjoy, then we know that's already going to be infected. Wait, hang on. Yeah, at the beginning. Okay, so we know that account's already infected. So let's say we have something like I don't know, 67, 68, 69, 70, and Killjoy's rating is 69. That's a 0. Killjoy's rating is 69 because I don't know why not. That's the sample. So then what we can do is we can add 2 to this, we can add 1 to this, and then we can subtract 1 from this. And the sum of these changes is plus 2. And so because this account is already infected, we can do whatever we want. We just need to make the rest of these equal to 69. And the way we do that is just to subtract 2 from it. And it's at least 2. Good. So if we have any account that's already equal to Killjoy's rating, then we just like win. We can do whatever we want to this, and we can make everything else equal to this rating. So in this case, if count is greater than 0, we just print 1. Otherwise, we can either do it in 1 or 2 operations. Let's say this was not equal to 69. Let's say this was, I don't know, 5. All right, so to increase this, we would have to increase it by 64. But we can't do that, so the next best thing to do is to make all of these 69, and then we just add the residue, which is plus 2, or minus 2, I guess, to this. Then this will be 3. But then now everything is 69 except for this one, so what we can do is we can add the plus 66 we need here, and then just subtract it from literally anywhere else. So then we can do it in 2. However, there's another special case. Say we have this. Then the sum of the rating changes is automatically 0. So in this case, we're just done. Like, we're just done. We can always do it. We can do it in 1 because by definition, that's like the operation we use. So we can do all of it in that operation. So we just need to check all the differences. If sum 0, then we can do it in 1 operation. Otherwise, we have to use 2. Huh, nice. 102. Okay, we'll do one more. 1. So we'll do like 3, 5, and then 7, 7, 5. Yeah, because we can make these 5, and then we can make this 9, and it should work. So the values themselves don't really matter. It's just if they're equal to k or not, and then eventually there's sum. I think that works. Still in Q. 2 free tests for everything. Okay. Interesting. Interesting. So now we get rid of test cases here. Have number n. Okay. So all the prices are different. Here, all the prices are not different. Or not necessarily different. This version. Okay. What's the difference here? All n ice spheres are placed in a row, and they're numbered from 1 to n from left to right. An ice sphere is cheap if it costs strictly less than 2 neighboring ice spheres. The nearest to the left and the nearest to the right. Leftmost and the rightmost ice spheres are not cheap. Sage will choose all cheap ice spheres and buy only them. Okay, so this one should be simple, I think. We'll do the easiest subtask first because it should go down like very easily. Basically, what we do is let's say we have 6 positions. Only positions that can be surrounded by 2 elements are like possible to make cheap. So we can, for example, mark this position and then mark this position as well. And yeah, and then we can say this is the answer because we can't have any more cheap ones. And then we can like put the small elements here. We can like order the elements. So first we put them in cheap positions, and then afterwards we put everything bigger in other positions. And this will work just because like all prices are distinct. So we basically just put these here. Yeah. Okay, so let's say like bool mark. What's the input? 10 to the 5th. Okay. So for LLI, all right. How this work? Okay, now what? Kind of do like a 2-pointers thing where if mark AI, no, mark I, then bi equals b or a endpoint plus plus, else bi equals b end mark a, then cout end mark and just print everything. So this is the easy version. Should be quite simple. 31425, perfect. We'll test 6 to make sure it works for even numbers. Oh. 618394, perfect. Wait, what? Oh, that is good to check. Yes. Glad we didn't submit that then. So this and that and everything else is fine. And 5. Yeah, okay. Good. This is just D1, just the first subtask because why not? It's free points. Might as well do it. And we figure out the rest. How are we doing right now? Can't imagine it's that well. Whoa, wait, what? We had a terrible A. How are we doing this well? Jesus. What was C? C was just the... C was just that. Okay. C was just this caseworks. Okay, don't delete all the code. But now we have to figure out how to do D2. Because that's worth more points, and it's probably better to solve, so we should do that. And how do we do that? So I think the same idea should still apply, except I feel like it should be a similar idea somehow. Well, I'm not really sure how to like do it. So we keep marking positions, and like the only problem we have is that what would we do here? First of all, we can notice that the answer is like binary searchable, but I don't think that helps. Also, OP typing. So you put an element like here, and then like here, and then like here. It's like if everything's what we do for this, something like 1 1 1 1 1 3 3 3. Then what we can do is we have 6 positions to put it in. So we can try the same alternating strategy. I'm not sure if it would work at all. We can do it like this, and that would work. Say we had an extra, or say we had like this instead. Then if we arrange the elements like this, well, no matter what we do, we're kind of scoring ourselves out of this anyway. Because we have like too many ones to place down, I guess. That would be it. I feel like a similar strategy would work. On the even positions, we put down the lowest number possible, and then we kind of like enumerate the odd positions. Although I'm not sure if there's some better way that lets us do better. Because like this is going to be the smallest number, this is going to be the next smallest, this is going to be the next smallest. And this is going to be yet again the next smallest. So if even this number is equal to this, then we have like a lot of ones. So no matter what we do, we're going to end up being screwed out of a lot of positions. And I think this way lets us like screw ourselves out of as few positions as possible. This is not a proof, so I'm not actually sure what to do. Yeah. Intuition just like says it should work though. I gotta try and find a break case for this. AI is greater than AI minus 1. This code we have to write anyway because we have to AI is greater than, because it's just counting the number of marked positions anyway. Like this is gonna work for this sample, but I don't know if it's gonna work for everything. It's not even gonna work for this sample because n mark equals 0. Yeah, we gotta do that. It should be B, not A, because if it was A, because the array is sorted, there's no way we could have any of them. 2. Why? BI is greater than BI minus 1, and BI is greater than BI plus 1. Huh? That does not make sense. It should be, wait, that should be less, whoops. Less than and less than, yep. Okay, so that'll work for this sample, and that seems to be the exact construction they use, but it seems, maybe it's misleading on purpose. Like here we can get all 3. 6, 1, 1, 1, 1. I think the answer is constrained to 1 in this. Yeah, because there's only one cheap thing we can have, because we only have 2 3s to give around. That looks optimal too. This should be 3. I don't know. That's the thing. Because we could have like a lot of big things. Or like a lot of... I'm not sure. 1, 1, 1, 2, 4, 5, right? We have a lot of elements bigger than 1. How does this work? Okay, that's clearly optimal. What if you have like a lot of things in the center? Does that still stay optimal? I think it must be. Okay, I may be wrong, and I may get a wrong answer right now. Just like intuitively feels right. Well, again, it may be wrong. Okay. Alright, we're doing pretty well right now. Now we just gotta get E and stuff. I really don't know why that's right, actually. I guess there's some way to prove that it's optimal, or I'll fail system test, one of the two. Yeah, that would be interesting. Wow. We're doing like remarkably well compared to a lot of other people who are not solving things for some reason. I guess A was also rough for some other people. Okay, anyway, oh boy, circle problem. Okay, given test cases again. You have a composite number n. All divisors of n are placed in a circle. Huh. One move can choose 2 adjacent numbers and insert their least common multiple. Okay. You can do that move as many times as needed. A message is decrypted if every 2 adjacent numbers are not coprime. Not coprime. So they share at least one divisor. Okay. Find the minimal number of moves cipher should do to decrypt the message and show the initial order of numbers in the circle for that. So the LCM of all divisors of n has to be n, which means that in n operations, well, actually, obviously, in n operations will be done because there are no adjacent elements, so we automatically win. I feel like the answer is low for this. How's this doing? Or have many people solved E? Okay, not many. So we have a lot of time to go for this, and I think we should be 14th for a while until people start solving E again. So that should be fun. How are other people doing? I wonder what the solution to D1 would be that doesn't work for D2, because I basically had the exact same thing both times. Actually, yeah, it was the exact same thing both times. If you resubmitted my D2 solution, it would work for D1. So I'm not actually sure what it would be. Okay. So what do we do for this? So we have like 14. Right? Then we have 2 and 7, so we have to have that. First we can write code to get divisors, I guess. Okay, that is just code to do that. Well, we'll keep them unique and see how divs. Just make sure that worked. One, two, three, six. Well, so we're guaranteed that n is composite. It doesn't matter that much. 2, 3, 6, 2, 4. Yeah, okay. So now what? So how do we construct the divisors of a number? What we do is we break it into prime factors. For example, we have 2 to the 7th times 3 to the 3rd times 5 to the 2th, yeah, times 7 times, I don't know, 13 squared or something, right? And we can do it like that. And then basically every divisor is going to have some subset of these numbers. For example, we could have like 2 to the 6th and then times 3 to the squared, and then we don't have any 5s, and then we can have times 7 and then like 13 to the squared, and that can be fine. We can have any number as long as it doesn't exceed like these. For example, we can't have 2 to the 8th because that's like not possible. So what happens here? Say we like also there are most log n prime factors, this is known. You know, I have a number theory template for getting divisors. I don't actually know why I wrote this manually. And I might have to bring that number theory template in anyway, so what does it matter? Okay. So one thing to note is that this 7 is like almost everywhere. In fact, exactly half of these divisors have the 7, and the other half don't have them. And that is because, like, that's just how it works. Take all the divisors that don't have any 7 in them. Right? And then you can get a new divisor from every one of these divisors by just multiplying all of these by 7. So half of the divisors don't have 7s, half of them do. And Basically, we kind of just need to bridge this gap somehow. If we put all of these together and then all of these together, then all we need to do is to literally link these, I guess, on both sides, because it's a circle. And then we'll be done. So we can break them into prime powers, I guess, and then we can say, like, if we have this, then we have 3 groups that we have to, like, we could have no 7, we could have 7 to the 1, or we could have 7 to the 2, and then we have to link all of these groups together. And how do we do that? Well, the annoying part is that we can't consider 1. Is that annoying? I feel like it's not annoying. Well, so this group is special, actually, because it doesn't have 1, while everything else could have 1. Like, we could have 1 times 7, or 1 times 7 squared, but we can't have 1 times 7 to the 0, because that's just 1. And we can't have 1, because, yeah, that's, like, the definition. How are we doing on solves? Okay, more. More, but not too many. We can still do this. We can still do pretty well, I think. We're only, what is it, 60, wait, 59, damn it. We're only 59 below the next, actually wait, no, sorry, 159 below the next best guy. That's a slight difference there. Other than that, we're doing great though. Whoa, that's a big delta. Yeah, so now we just have to like figure out how to do this. Indeed, how do we do this? How do we do this? But actually, all of these groups are automatically linked because they all have 7 in common. So it's actually only the group with no 7s and everything. Yeah, it's actually only the group with no 7s that we have to link with everything else. Also, this drawing is incredibly messy, I just realized. But all of these are kind of the same because they're already linked by 7s. So all we actually have to do is link the things with no 7s to the things with 7s. And so therefore, the only things that could contribute to the answer are the 2 barriers. And what? And what? Okay, let's say we have, what did I do? Let's say it's a number like this. So 3 times 5 times 7 to the 10th. Okay, so the possible divisors from just this are 3, 5, and 15. So what we can do is we can kind of order the groups like this. So we can do 3, 5, 15. And then we can do 15, and then whatever here, and then on the other, or actually we can do 15, 5, 3 here, and then on the other side we can do like 3, 5, 15 backwards. And we'll say this is times 7, and this is this is what? What would it be? It would be like times 7 squared. And so in terms of constructing an array, we can put these divisors first. And actually, we also have to have a 7 here and a 7 here somewhere. So we can just like stick that in. In terms of constructing an array, what we can actually do is even simpler. We can just make all of these backwards. Because like it doesn't really matter what else we do. right? All of these are multiplied by 7, all of these are by 7 squared. And so this edge of the circle is going to have this, and this is going to be connected, and everything else is connected by 7s. So we just win here. This is enough. So now what we actually have to do is we have to break. So I think finding the direct divisors is kind of useless. What we actually have to do is we have to break n into a bunch of prime powers. And once we do that, we make this exact construction, and then we can literally just check everything. Yeah, we can check everything. So I think with this construction, the answer is either 1 or 0. Either 1 or 0. Because of the fact that like we can automatically bridge this first gap. We can just like put whatever number we have at the end of this block right at the beginning of this block. So what matters is if we can bridge this gap. And sometimes we can't, sometimes we can. And I don't think we have to do any casework for it. Like either we just directly make the construction and then we see what we can do. So now what we have to do is number theory. What I should do is add to my number theory template. Okay, so I think this whole thing is actually useless that we wrote at the beginning. Yeah. So first we'll do gem primes. Only 6, because why not? Just a big number. Time limits 1 second. So we can be a bit more fine. All we need is the prime factors that are less than or equal to n. So what we need from this template is this. And what we want to do is we want to make it a map. And that way we can get the exact prime factors. So this should be this, and okay. What do I call it? Get facts or factors. Just testing this out to make sure. Oh my god. I don't like my own template anymore because it uses my pre-written code for everything. But I don't have that anymore. Pretty sure I like actually said that I would fix this before and then I haven't yet, which is great. Bool primes generated, vector, LO. Yeah. This is stupid. This is very stupid. Don't be like me. Make your templates work. Let's see if this compiles now. What? Pushback. Okay, 2 to the 1, 3 to the 1, 5 to the 1. Perfect. And let's do some like bigger number. Like, let's actually do this out. 2 to the 7th times 3 to the 3rd times 5 to the squared times 7 times 13 to the squared. You can make this 7 squared actually. No, let's just do that first. And this is of course way too many numbers to actually think about. I just want to make sure this like actually works. 2 to the 7th, 3 to the 3rd, 5 squared, 7, 1, 13 squared. Perfect. Okay, we're good, we're good, we're good. comment that out in case we need it again. We can leave it there. Okay. Now what we want to do is, basically if we choose the prime factor with the least amount of occurrences, then that will guarantee that we can optimize the construction. So tar equals 0, count if x dot second is less than t count, then this is a better one. So t count x dot second, tar equals x dot first. I think we could still use this actually. Now I want to generate all the divisors that are less than n. That's what we want to do, right? We want all the divisors that are less than or equal to, we want all the divisors of n that aren't 1 and that aren't divisible by tar. And then okay, so we actually do need the divisors of n, so I kind of played myself here. Yeah. Should I vector yeah, I definitely played myself. Push back. And I want to explicitly exclude 1. This get unique is a template function I have that's, you can check it out. Basically just gets the unique numbers from a thing. I can't remember it for the life of me, so I just put it in my template. Vector ll divs equals. Okay, so it turns out the code I erased before actually is necessary. So that's cool. How do I do this? Let's not be an idiot. Let's just stop being an idiot from here on out. Okay, perfect. So now vector llx if x mod basically we want to exclude target. It's not equal to 0. X dot push back x. Now for ll now we just make the construction basically. Circ dot pushback. If I is greater than 0, circ dot pushback p, and should be a semicolon. Circ dot pushback p times I. No. X I times p. and this is the construction we want, then for LLX circ, just print it. Should be circ.size. Yeah, and then if we'll just take the LCM, circ I times circ ni, LC divided by this is a standard formula. If LC the 1 plus plus ants. So this is only going to happen if we have like exactly one other divisor. So I'm pretty sure that like we can always do it in at most one operation. And like the fact that we like combine things is not a big deal because we can then like say we have 2, 7, 14, right? Like I feel like this is one of the only cases, and then we just combine this to get 14, and then these numbers are not coprimed, so we're happy. So it's only the answer is only the number of elements that are different, or that are only the number of adjacent elements that are coprime. That's a lot of what the hell? Okay, come on. I don't think we get to the circle point. So let's do x. See out circ. We know x has to be of size at least 1 because it's coprime. That's like the definition of. Alright, printing endo because it doesn't print segmentation fault. So this is just empty. 362, 362, 0. That's a problem. That alone is a problem. Oh, wait, this should just be GCD actually. I don't know what I'm doing. But why is this empty? 4 is, oh, it's a prime power by itself. I think that's a special case. So in this case, the map size is 1, so we just automatically win. We should test more edge cases and stuff. Oh, wow. Okay, I see the problem. I think I do see the problem. And there should be some slick way to fix that, I guess. Okay, the mistake I'm making is that now we have to like, okay, I didn't realize this was a thing, but now we have to make it so, like say we weed out the 7s, alright? So we have some stuff 7 here, 7 squared, whatever. But now we have to order these elements in a way to minimize the number of like collisions, whatnot. So that's fun. How do they do it here? 3, 15, 3. And huh, okay. I think we have to do this recursively. Let's see, divs vector. How would count that size be 0? I don't think that's possible. It should be 1, not that. Yeah, they shouldn't have 1 either, so that's fine. So what we do here is count.erase targ. And then do something like this. Solve excluded count. So we do this recursively. And then we return circ eventually. So here's what we start with. We start with circle. If we have exactly 1 prime factor, we just generate all of the powers and then we're done. Then we find the thing with the least number of occurrences, I guess. Does it actually matter? I'm not sure if it does. Don't think it matters if it matters, because this is login anyway, so that's fine. Number of excluded values, then this is basically just checking all the divisors, and yeah. And then we solve with the ones that don't have that, and then we use that ordering to construct the ordering with this prime factor, and then, yeah. Vector ll circ equals solve divs count. I'm not sure. This should not compile. All of these are negligible. It's just signed and unsigned. Great. What's with that? Indeed, what is with that? Why is it 1, 2, and 2? It makes negative sense. going on here? What was that? So 2, 3, 6, right? And then 3. What do we get from this? Why is this 1? Oh, next up first. That would be important, I suppose. What happens here? This might be like fundamentally broken. That would be a problem. So 1, 2, 4, 0. And we get 2 and then 3. How would this work? So we have 5, 15, and 3, right? And then after that we have 10 and 2, 30 and 6. Oh. We didn't actually do what we were supposed to. We're supposed to reverse this. And that makes it work. Because that's the construction we were talking about. Okay, so the answer for this should be 0. Although I'm not really sure what to do with it. Nice. Okay. Because we self-check the answer. So like this is the answer. If we're getting the answer to be 0, that's right. So let's try 2 to the 7th. 128. 128. Easy. 1 2 to the 7th times 3 to the 3rd times 5 times 5. 17, 280. That's useful. So we do all this. And then we do 128 and then 3 and then all this. I think it works. I think it should work. Unless there's some special case we're missing or something. That would be annoying. Okay, that's good. Not doing terribly. So now we have 50 minutes and we have to get F. I feel like the implementation for this could have been smoother if we thought it out a bit more, but whatever, what can you do? It is how it is. And still doing fine. Shoot, I got rid of the whole solve function. Kind of need that. Get rid of number theory though, unless we need it again. Let's check F. Is it number theory? It is not number theory. Okay. Or maybe it is, but it doesn't look like it from an initial glance. Okay. So where are we right now? We have a pretty good time on A to E. And we are in 27th. So now it's going to depend on F. And because we have no mistakes, like this rank should be relatively secure, unless F makes a difference, which it might. But one person has solved F so far, none of the LGMs have. So we'll figure it out. We'll see what we have to do. How is the time actually? Because this is technically n log squared n, which means it's actually crazy that it ran that fast. Cool. Wait, is it n log squared? Actually, no, never mind. What am I saying? It's log n squared. Yeah, what am I saying? Okay, it's like the number of test cases times log n squared. So that's whack. But yeah, that was a cool construction. I like that problem. I enjoyed struggling with it. Okay, he's got to. Alright. There are n detachments on the surface, number from 1 to n. The ith detachment is placed in a point with coordinates xi, yi. All of them are placed in different points, so we get 2D points. Brimstone should visit each detachment at least once. You can choose where he starts. He can move in the 4 cardinal directions, and that's cardinal, right? Directions. Yeah, 4, okay. So he can move in the cardinal directions and start moving with a constant speed of 1 unit interval in a second until he comes to a detachment. Huh. Each t seconds, an orbital strike covers the whole surface, so at that moment, Brimstone should be in a point where some detachment is located. You can stay with any detachment as long as needed. Good commander, that's why I can create at most 1. Okay, so that you're not trying to minimize the time, which is good, because that would be, like, hard. Instead, we need to see if it's possible to visit everything. Yeah. Rain of fire. So people are getting TLE, which makes me think it's like n squared log n or something. Like time limit exceeded. Time limit exceeded. Let's see. How is status for F? So TLE, is he about to get it? I think he's about to get it. Yeah, TLE, okay, actually these time limits are short. I mean, these run times are short, so maybe there's something better. That took a while. That TLE'd. And a bunch of other people. Okay. There are 4 samples, nice. So, basically you pick a point, and then you build a minimum spanning tree over those points, where the only edges you can make are vertical and horizontal ones. That will take n squared log n time. And once you do that, then the t required is... Okay, let's clear all this. We'll get back to that mess later. So for example, the first sample is like this. It's a cross and everything is 100 apart. So the optimum place to put the t is here. Then the minimal spanning tree will be like this. And then that works. Right? Yeah. And then all these are 100, so at any point you can move like 100 each. You can stay with any detachment as long as needed, and that's fine. So... Does it work with this format? Let me just know. Okay. Is there anything here that looks nice? Ugh, okay, whatever. So what's the third sample? Third sample is, let's see. So you have some at 0, 0, 0, negative 1, 3, 0, negative 2, 0, and negative 2, 1. So this is 2. This is 1, this is 1, this is 3. So the optimal thing in this case is to put this right here, or in one of these two spots. Then that will cut this edge in half, and you'll have something of size 2 here, or something of size 2 here, and this is also 2, so that's the best you can do. Let's put it at an integer, right? Yeah, integer coordinates. So it has to be, answer has to be an integer. You can't divide it in half. So this is kind of a game of components right now. Let's say you make connected components between all of the points, and then, interesting. So if you make connected components between all of the points, you get something interesting. Because let's say I put T, or not T, what is it? I put the new attachment here. Okay, now say there's a connected component up here, and there are some points that are attached to it. Then if there's also a connected component down here, that putting this here would merge these two, well, that wouldn't be possible because these would already be connected by this edge. So on one side or the other, we can only have one connected component above this T. And similarly here, if we do this, then we can't have a connected component on both of these sides because then these would already be connected. So at most, with the new detachment we put in, we can merge at most 2 components together. So if we have 2 components already, so if we have more than 2 components, then we no answer. Otherwise, we can always merge the 2 components together. So if we have 2 components, then we can always merge them together. And the question is now, how do we do that? And I think the 2 components should be independent of each other because, well, clearly. Okay, here's where it gets hard. Indeed, here's where it gets hard. Because we can't just take the minimal spanning trees. That's not enough because for example, we could take this as an MST. let's say this distance is 1 or something, right? But then via like some method of is the MST optimal? That's another question. So we consider any 3 points. Either they're like they don't care about each other, or they form something like this, or they form something like this. In this case, all these edges are independent, so we don't care about this. So we're more interested in this structure, I guess. In which case, the edges have to be like this, and then I guess it'd be optimal to cut the larger one. If you have 4 points, this is where it gets more interesting, because either of these longer ones you'll have to cut somehow. How is the question? That is indeed the question. How do we answer that question? That's the problem. Check how we're doing again. Are more people solving E or F? Okay, we're 28th, which is not bad. We have only 6 people. 9 people have solved F so far. I think E was kind of like implementation heavy. Maybe that was my solution, was implementation heavy. So it could just be that people haven't had enough time to start attacking F, and now that they can do whatever they want. There's some intuition to be had here. I wonder if we can just take any arbitrary MST. Actually, no. The problem would be to consider these 4 points where we kind of just duplicate them. The problem would be taking this as an MST, something like this. If we take this edge instead of that one, it's symmetrical, I think, and versus this. Would that even happen? It seems like it wouldn't. So Kruskal's algorithm, like by definition, minimizes the maximum edge on the MST. It also minimizes the sum, I believe. Should. I think there's some proof for that. But the fact that it I don't know how MST works, but the fact that it makes some minimal edge is somewhat interesting. Alright, that should be easy to observe because it's just like greeting all of the edges. And if you can make a component, you do. And if not, then that component couldn't have been made. So it's kind of very bad proof for Kruskals. Yeah. Okay, I don't know what I'm talking about. So what's this one? Let's think about the 4th sample. So 00, x equals 2, 0, 0, negative 1, negative 2, 0. Oh, we have this. So we have this at 2. We have this at 2 instead of 3, which is the difference from this sample. And now, because these are 2, we have too many of these edges, so we can't really do anything. these cases are separate, where we have where we have two components and one component. If we have one component, then well, we can do coordinate compression. What does coordinate compression do for us? With coordinate compression, we can essentially say that like we group all these together. So there's only one spot between them, but we say this spot is 2 wide, and so is this one. And this spot is only like 1 wide. But there's still only one spot between all of these. Actually, it doesn't change anything here, but if we had something like, for example, 7,000, it would still only be one spot in between. That would be how the compression works. So we say that difference is 70,000, or 7,000. But that's weird. That is weird. Because we do care about the distances, actually. No, sorry, what we would do is we would say this, it'd be like the gap between these two. This is 7,000 wide, not the points themselves. I think. That's still weird, though. Because we have to consider putting a point like between these two, for example. I don't even know if that would help. Would it? Okay. Get a slight break because this is too much at once. Just think about this for a bit, I guess. So apparently I don't know how to open my own bedroom door. That's a fun observation. Okay, in that time, how much have I gone down? Are people actually solving F? Okay, we're at 11 solved, so this is not easy. But it seems like ABCD is the way to go for most people. Then E is harder, you just have to figure that out. And or F. How much is F worth right now? Eventually its number of points is going to degrade to as much as I got E for. And then anybody who gets F without E will be screwed. Anyway, that's not really relevant. What we should do right now with these last 28 minutes is try to solve this. So, how do we solve this? Yeah. Let's say we have one component. Is that easier? We have one component. Like, there's some edges we absolutely have to have and some others that are kind of optional. But decomposing the graph into cycles is not something I want to do. So let's not do that. Although for an example of what I'm talking about, like say we have something like this, then all of these edges are necessary. But then if we like stick on some like, I don't know, like this, then we can have any 3 of these edges will work. Because all we have to do is connect these points. But of course this could be even more complicated. Like say I put some more points down here. Right, and then we have like a huge cycle. This whole thing is a cycle. And so is this. And so is this. And that gets very complicated. So specifically analyzing cycles is a terrible idea. And that can't be the way to go. So far the other problems have had like nice solutions. So I think maybe this one might too. I don't know. Actually. That's not a good thing to think about. We should just find any solution, whether it's nice or not. Let's save a bunch of points like this. This is kind of the trial period where we're trying to just make any observations we can. And then we'll use those eventually to form something we can work with, and that is how we get to a solution. Unfortunately, I'm not getting anything. So this trial period is not working out. So we know when it's not possible. That part's fine. And again, we still have 2 cases. Either we have 2 components or we have one component. If we have 2 components, then we have to pick 1 point from component A and 1 point from component B, and then we have 2 locations or 1 location. No, we have 2 locations because they have to have different x and y. We can either put the new point here or we can put the new point here. And if we can efficiently check the value of t for all of these new points, then we win. And Um, Otherwise we don't. So were this a normal like graph problem where we're asking if we can add one or two new edges, how it would change the minimum spanning tree? I think like that should be well known. Actually, the problem for one edge is well known. I don't know about two edges. Two edges is harder. But this isn't even a normal MST problem. The harder part is that we could possibly, like say we have 2 points from component A, we could, when we add this point, we split this edge in half. And we add this new edge. So that's even worse. This is equivalent to removing an edge and adding now 3 new edges in. So we can't use like standard tricks for that, especially because it's even more complicated than it would seem. Instead, what can we do? Instead, let's check the standings. Oh, someone in my room got F and they're going backwards, I guess, for some reason. Nice, second threads in my room, nice. Still 28th. Okay, this is not changing much. 3 more people have solved F. In 6 minutes? Okay. Not giving up, but I don't have the most of confidences. This is, however, an interesting problem. And or a hard problem. Feels like it could also definitely be possible to do some sort of like data structure cheese on this or something. But I don't know any data structures, so can't do it that way. It's probably not cheesable, actually. I would imagine it isn't. Um, okay, something else. Maybe there's something better. Problem is there are many different minimum spanning trees. Although say we do build MSTs on this. So we build an MST on this one. Like most of the edges are gonna stay the same. For example, we can have an edge like this and an edge like this, and that's it, basically. We can split at most 2 edges. Huh. Wait. That is kind of interesting, because we can split up most 2 edges, specifically the biggest one and maybe some other one. So actually we have to try, if we have one component, we have to put the point at the biggest edge. I think that should work. but there's more stuff to be had here. I think that should work. I also doubt I'll have time to implement this. Because, okay, so the harder case seems to be when there are two components. And why is that the harder case? Because now there are a lot of points to check, right? Actually, you can take any 2 points. If you take any 2 points, one here, in different components, then this edge is going to be delta x, and this edge is going to be delta y. So automatically the new edges are at most this size. And then what? I'm what indeed? Not even sure if that works. Because the MST is like, there are many possible ones, I think. 12 people on top. There's a madman's notes right here. So here's my problem, right? We have something like this, where we have something like this, and let's think of this weird construction. We have this here and this here. So let's say all of these are 1 apart. Like this is 3. This edge is mandatory. Then we have to draw this one, we have to draw this one, we have to draw this one. And now we have to figure out how to unite these points. If we make these 2 edges both with distance 2, then Well, we can't do anything. There should be some counter case to this. Like, say this is not 3, in fact. Say this is like this. So we'll take this edge, and then this one. So this is, maybe this is like 13, and this is, I don't know, 2, 2, 2, 3, 1. So now both of these edges have equal possibility of being taken, but only one of these edges leads to the answer. If we take this one, then we can split it, so this will be at weight 4, but we can split it into two edges of weight 2, and then the answer will be 11. And in fact, actually, let's make this even clearer what's happening here. We'll make this edge weight 4. And so we can move the red point closer in, whatever you want. The point is this section is 2 and this section is 2. So either we take this edge, then we split this into 2 and then the answer is 3. Or we take this edge. Then we can't split both of these 4 edges. We can only split one of them, so we lose. And with the minimum spanning tree, these choices are arbitrary. Like, we don't know in advance that we have to take this one to get an answer. We have, like, equal chance of taking this one and taking this one. So if we have cases like this where that's replicated, then just taking the minimal spanning tree, minimal, whatever, isn't going to work. Which means I kind of just disproved my own solution, so that's sad. More people are solving F. How many more people? It's not easy. Okay. Second thread being Java'd. You might definitely be being Java'd. That's a possibility. How goes the room? Has anyone solved? One person has. And it's an IGM 2700. Probably even more. So that's not happening. Also an IGM. Who are the people that have beaten me? Okay, he's been GM before. Yeah. And only one person in my room has solved it. So this is not easy. This is not easy. Wow, more people are solving it by the second. Do we have any chance of getting this at this point? We have 10 minutes, and I kind of just destroyed my own idea with an edge case, with a counter case. I don't think we have a chance. Yeah, with 10 minutes, there's no way we're solving this. Okay. In that case, I will get to the solutions then, because I have nothing better to do. And yeah, I don't have anything better to do. So we'll settle with whatever rank we get afterwards. Probably worse than 34th. As more people begin to solve this. Yeah, I don't really know what to do. Okay. Let's do the rest of the problems. So we have A, B, C, D1, D2, and E. I might do D1 and D2 separately. I'm not actually sure. Actually, my solution that I came up with basically solves both of them. So I don't understand why D1 was easier, actually. Maybe it gives you a way to check your idea, I guess. But then D2 is kind of just an extension of that idea. Okay, whatever. So check my place one more time and then be done. Be done. Be done. Done with it. Done with this. What changed? Okay. Alright, we're doing A. So we have a n-digit number, for example, 2069. And there are two players that are going to play a game on it. One player can only take from the digits at odd positions. So I'll number these positions 1, 2, 3, and 4. And the second player can only take from even ones. The game will go as follows. Every turn, the first player will mark one of their digits. They'll like cross it out, and then that digit doesn't matter anymore. And the second player will do the same. And then the first player will do the same until there's exactly one digit left. And in that case, then what happens is if the last digit is odd, the first player wins. Otherwise, if it's even, the second player wins. So you have to figure out who's going to win the game, basically. So first of all, the odd and even positions are completely independent of each other. So we can just kind of like break these up into separate groups. So we have 2, 6, and 09 here. And then, more importantly, the last turn is fixed. If n is even, then the last thing will always be the second player, because there'll be an odd number of digits to remove, and that will be the first player will remove the last one before there's only one left. So the second player will have a choice of what happens. Otherwise, an odd, then the first player has the choice. Now, let's say the second player is predetermined to have the choice. What's the best solution for them? Well, they want the final number to be even. So they might as well remove all the odd numbers right off the bat. And then all they'll have is even numbers. So no matter what, if they remove all the odd numbers beforehand, then they will always have an even number to finish with, regardless of what the first player does, because the first player can't affect these digits. So, however, this is only possible if there's actually an even number in the first place. If the second number only has second player only has 9 and 1, then no matter what they pick, they're always going to end up with an odd number. So if they have greater than 1, even, win. Otherwise, if they have 0 even, then they lose. And this is the same condition, except now everything's odd because they want this to be odd. So if the first player has greater than or equal to 1, that's odd, then they win, because they can take everything except for that number, and then that number will be the last one, so they win. Otherwise, if they're 0 odd, then they lose. And this is kind of the decision tree for how this game is going to play out. So, yeah. And the only special case is when the first and second player don't even get a choice at all. For example, if n equals 1 and this is 2, then automatically it's over. But you can notice here that this is the first player's turn, and they don't have an odd number. So even though they don't get a choice, this casework still applies, because this is still there are no odd numbers. So automatically it ends with an even number and the first player loses. If this is 3, then even though they don't get a choice, it's still an odd number that they win through. And similarly, if there are 2 digits, then the second player only controls this 3, so the first player is forced to remove this, and the second player doesn't have an even number they can leave, so they lose. So even if n equals 1, and even if n equals 1 or 2, and the players don't get a choice about what they remove, this casework still applies. So this is essentially it. You check this kind of decision tree, and then this is second player wins, second player loses, first player wins, first player loses. Equivalent to win 2 and win 1. Yeah, that is the casework. Okay, that would be A. Now we're on to B. B's weird. B's very weird. Okay. You have a you don't have a staircase. Consider a staircase of n steps. For example, 7. And, well, actually, I'll wall it off from below too. And basically, you want to fill this staircase with squares. So, for example, you can make this red square, which is 4 by 4. And then you can make these two blue squares, both of which are 2 by 2. And then the remaining are 1 by 1 squares, etc., etc., etc. So you have 7 squares in total, and you have 7 steps. So you want to basically check I'm going to basically check if it's possible to make a staircase with n steps, using n squares. This should be n, not some other letter. Using n squares. And if so, then this staircase is, let's say, good. What do they call it? They call it, like, beautiful or something? Or nice. We'll say nice instead. Yeah. So staircase is nice if it has n steps and can be filled in using n squares. So for example, let's think of another staircase with 5 steps. So let's say we put a square so in this construction I automatically put a square at like the midpoint. So let's say I put a square somewhere else, like for example here. This just kind of screws you over, because now you have to fill in this one, and now you have a staircase of size 1 and a staircase of size 3, and you've taken 2 squares already. But instead, what you can do is you can use 1 square, and then you have 2 staircases of size 2. And it's just like better. That's kind of it's always the best option to put a square like in the middle. So we have like 4 steps where we can't do that. 2, 3, 4, and we make the staircase. Then like we can't even put it in the middle. We can try putting it here actually, that would work. And then we have 2 staircases of size 2. So actually this is the same as 5. 4 and 5 are the same, and I imagine 6 and 7, 2, 3, 4, 5, 6. How many would 6 be? So for 6, you would make this square. And you have 3 stairs of size 3, or 2 stairs of size 3. So essentially you have the recurrence of f of n is equal to 1 plus f of floor n over 2, I think. Okay, and so kind of doing this out, you'll see that, like, for example, 1 will take this many. Let's just fill this out up to, like, 7. 1 will take that many. So 1 will take 1 square. Fine. 2 will take 3 squares, actually. 3 will also take 3 squares. Like this square, that square, that square. 4 will take 1, 2, 3, 4, 5, 6, 7. So 7 squares. 5 will also take 7 squares, and 6 and 7. So looking at this recurrence, these two are going to rely on this one, and these two are going to rely on this one. And so if we consider like filling it out for 8 and 9 and etc., like the first two are going to rely on this, the next two are going to rely on this, and the next two are going to rely on this, and so on. So they're all going to be the same, and they're all going to be 15 ... and then we're going to have 31s ... and like 63s ... and so on. I'm not sure how you would get to this. I assume the way to do it is just to like kind of do out some casework and realize this is a pattern. But basically, the only times it's possible is at the ends of these ranges. So for example, like this, and then this will be possible at 15, this will be possible at 31, this will be possible at 63, etc. And thinking about these like more carefully, like this is 1, this is 2, this is 4, this is 8, this is 16, this is 32, etc. These are powers of 2. And so basically, the number that's like, any number that's like a prefix sum of these powers of 2 will work. Specifically, it's a number of the form 2 to the n minus 1, where n is greater than or equal to 1. These are the only possible staircases. So these numbers are 1, 2, no, screwed up already. 1, 3, 7, 15, 31, etc. And what we want to do is, now the answer is, we want to figure out the minimum number of tiles. We're given n tiles. And we want to figure out the maximum number of nice staircases we can make with that number of tiles that are different. So we can't have 2 staircases of size 1. They have to be different. Like it has to be 1 staircase of size 1, then maybe 1 of size 3, then maybe 1 of 31, but then we can't have a 3 again because they have to be all different. So I'm going to figure out the number of staircases you can make. And n is like 10 to the 18th, so you can't just brute force all numbers and check if they're of this form. What you can instead do is brute force all numbers of this form. So first, we can say we have 0, then we add 1, then we add 2, then we add 4, then we add 8, and so on, until we get to a number where, until we run out of cells, basically. And it's good enough to like do it in increasing order because the number of steps it takes is like strictly increasing. So like it's greedy basically. We make the staircase with the smallest number of steps possible, and then we make the next smallest until we run out of tiles. And so the number of tiles it takes is 1 plus 2 plus 3 plus ... plus n. This is the triangular numbers, and it's basically equal to n times n plus 1 over 2. This is a well-known formula. You can probably search it up on the internet and find out where it comes from if you want. The idea is you basically pair these numbers together, and then all of the numbers have sum n plus 1, and you have n pairings, and you have n over 2 pairings in total, so you multiply those. It's a bit weirder when n is odd, but it comes out to the same like values, so it's fine. So you just basically like check all of these, and so basically check 1, check the number of tiles to make 1. If you can take it, cool, keep going. Check the number of tiles to make 3. If you can take it, cool, keep going. 7, 15, and so on. And it's just like greedy. And it works. Yeah, that was elaborate. Wow. What have I done? I should make this white. Okay. Yeah, that was weird. Paint. Alright. OP stuff. Okay. So that's B. We'll refresh all of these. Check my final place. How far did I go down? Oh, system testing. Okay. Whoa, he got F, like barely. Jeez. I guess we'll cover different solutions then. So if you want to know how to do F, check out Second Thread's video, because he just did that. And, yeah. So we'll do C now. C is kind of also caseworky, like A. And the way to do it is, here's the problem, first of all. So you're given a rating system. And, actually no. You're given, there are n accounts on some site, let's say Codeforces. And some accounts are infected. An account A will infect another account B immediately if they have the same rating. And after that, both A and B will be permanently infected. no matter what their rating is, even if they don't have the same rating in the future. You have one account that's initially infected. For example, this is the sample. And all the other accounts are not yet affected. However, if there's some other account with the same rating, at any point in time, this will immediately infect this one, and this will become infected. This isn't part of the sample, though. So, I think we're like Mike or something, and we're evil. So basically what we want to do is we're going to simulate a bunch of contests. And we can give each participant a different rating change. So for example, this can be -x, this can be +y, as long as the sum of all rating changes is equal to 0. And we want to find the minimum number of contests it takes to infect all of the accounts. How do we do that? So there are a bunch of cases. Oh, and also not all participants have to participate in the rounds, but that's equivalent to saying they can have a rating change of 0, and that's important. So let's say we have a case like this. This is one of the samples. So like 4, 4, 4, 4, 4, 4. Right, then like immediately we're done, because all these are going to be infected before we even do a contest, because they're all the same. So let's say X is the initial infected account. Then the casework is if all of them are equal to X, then 0. Otherwise, not. Let's just say not that, then we have more casework. Now, the cases are as follows. Say we have 69, and then we have a bunch of like other things, like 2, 7, let's say like 5,000, and another 69. So immediately this account is infected. And now we have to do at least one contest because these aren't going to be infected. So let's like take these differences from 69. For example, for this we have to add 67. For this we have to add 62. For this we have to subtract 49, 31. And however, these rating changes don't sum to 0. But this account is already infected. It will stay infected, and we can't change. We also can't make this account participate in the contest, which is kind of important. So this account's already infected, so we can do whatever we want with it, and this is going to stay constant. So if we make all of these 69, and we don't care about this account, then we can do whatever we want to this account. So we can essentially like sum all of these up, say the sum of these rating changes is y, and then we can make this negative y. And then the sum of all of these rating changes is going to be 0, and because this account's already infected, we can just do that, and then every other account will be infected in one turn. So if we have at least one occurrence of X, then we have 1. Otherwise, we have no occurrences of X. Then we have even more casework to deal with. And now, it's still not that many operations. Let's say, for example, this case. Here, we have to add 1 here, and we have to subtract 1 here. So like by the definition of the problem, if the sum of the required rating changes to make all of these 69 is already 0, then then we can do it in just one operation, because like that's the definition of the operation we do. So if the sum of the required changes is 0, then you can do it in one operation. Then if the sum is equal to 0, then one operation. Otherwise, the sum is not equal to 0. Then how many do we take? Say, for example, we stuck, what did I do? Say, for example, we stuck this thing 75. Right, then this requirement will be -6. We're also guaranteed that n is greater than or equal to 2. Otherwise, we wouldn't be able to do any operations at all. So there are many ways we can think about this. We can make this. We can make the first number equal to x, and then we can just subtract it from, and then we could subtract this rating change from some other one, and then we'll have one number that's equal to x. And then we can do the same thing that we did for this case, because now we have at least one number that's equal to x, and we've already shown that we can do this in one operation. So it's one operation to make at least one of these equal to x, and then a single other operation to do the rest. We can make all of these 69 and then apply whatever residue we have to this one. So this will take 2 operations. And 2 is the minimum we can get because obviously we can't do it in 0 because not all of them are equal. And we've shown that we can't do it in 1 because if we were to do it in 1, it would either have to be that we can dump the residue on an already infected account, or the sum is 0 so we can do everything in one operation. But we can't do either of those, so it requires 2 operations. And this is the final decision tree of casework. If everything is equal to x, then we do it in 1. Then we do it immediately in 0 operations. Otherwise, we have more casework to deal with. So if we have at least one value of x, I've shown we can do it in 1. Otherwise, we have 0. So if the sum is 0, we can do it in 1. Otherwise, it requires 2. And you can check all that just with simple pieces of code. So that works. Have I failed any system tests yet? We got A. Okay. Slow A, yeah. We were not doing so well at the beginning of this. What? People FST'd A? Wow. How did that happen? How did that happen? What did people do? Not really sure why that happened. That is weird, though. Has anyone else FST'd other things? I don't even know. Okay, anyway. Let's get back to the problems. So this is a D1 and D2 at the same time, because my solution was the same for both of them. And I kind of solved D2 at the same time, but just didn't prove it. So I submitted D1 first, and then later, confirmed my solution to D2 with a bit more thinking. We just got B, nice. And so yeah, you can see there's 8 minutes apart. Yeah. So here's the problem. You're given a list of prices, and we can basically rearrange these prices in any way we want. What we want to check is so let's say we have 7 positions where we can put the prices down. And what we want to check is we want to count the number of positions where A1, A2, A3. We want to count the number of positions where this is less than this and at the same time less than this. So A2 is less than A1 and A2 is less than A3. More specifically, we have that AI is less than AI minus 1. This is not an A, I'm sorry. AI is less than AI plus 1. And the things on the ends don't have left or right elements, so they automatically don't count. We can't count these. Which is nice for casework. So we want to find the maximum number of elements that satisfy this, and we want to print both that and the rearrangement of numbers. So that's cool. How do we do this? So first of all, we can't have two of these special numbers together, because if so, then this would have to be less than this, and at the same time this would have to be less than this. So that just can't be possible. Even if they're equal, neither of these would be true. So these special positions have to be at least one apart. And I wonder if I might fail system tests on D, actually. Because there weren't that many pretests. So that's possible. I think it's possible. That could happen. Other people failed system tests on this? Test 68, test 61, test 71? What happened? Are these hacks? I guess they must be hacks. We had a very bad A. Although we kind of caught up after C. Yeah, they must be hacks. Were there hacks? I don't think I can see that now, but I guess there were. Some people on the top had like, yeah, people hacked on A. That is weird. Hacked again. Nice. We solved D first and then just did like nothing else. Wow. Anyway, that's all irrelevant. So how do we do this? I'm trying to figure out like why my solution's right. It would be kind of important to describe a correct solution. I know my D1 is right. I don't know about D2. My solution is as follows. So you sort the prices first of all, like 1, 2, 2, 3, 4, 5, 4. And then you start filling them in, but you fill them in a weird order. First, you fill in the even positions. So 1, 2, 2, and then you fill in the odd ones. So 3. So 1, 2, 2, 3, 4, 5, 4. No, sorry, 4, 4, 5. I didn't even sort the array right. Okay, and the idea here is that only elements on the even positions will be candidates for being special elements. And the basic idea is this is the minimum element in the array. So if this is not a special position, then this must also be the minimum element in the array. These must be the same. And if that's true, then like there are a lot of minimums. Like over half of the array is equal to the minimum. So the intuition is that even if this doesn't make a match, then it wouldn't be possible to make a match with that anyway. And we already space out the minimums in the array like as much as we can. Okay, so actually this configuration is only a problem when like the frequency of some element is like, I think greater than or equal to n over 2 is the condition. Yeah, if we have 4 1s here, we have a problem. If n is even, it's a bit weirder. But it's kind of the same idea. Okay. Why is that so slow? It's kind of the same idea. Like, if this will happen, then no matter what, we're going to miss out on some pairs. And this is the only time where we're going to miss out on some pairs. We're going to get the rest of the pairs. So let's say n is odd. Then specifically, we're going to miss out if some element occurs greater than or equal to, no, greater than, strictly greater than n over 2 times. And actually, we'll think about it like greater than or equal to the ceiling of n over 2. Then the number of pairs we miss out on is then we lose like frequency of x minus the floor of n over 2. This is my strategy specifically. Otherwise, n is even. So then it has to be greater than n over 2. And then we lose out on frequency of x minus n over 2. So we can also think about this as like strictly greater than floor n over 2, and then we get the same kind of formula. So so no matter what, we basically lose out on frequency of x minus floor n over 2 with my strategy. So the number of pairs we get is if we have an even number of things, like for example 6, then there are only 2 candidate positions for elements. So the number of candidate positions we have is like the floor of n minus 1 over 2. You can think of it like that. Because for 7, this will be 3, which is what we want. And for 6, this will be a floor of 5 over 2, which is 2, which is also what we want. And it'll hold for all other even and odd numbers. So we get n minus 1 over 2 minus this quantity. And I guess the maximum of 0 and that, because we can't lose more positions. We can't have negative positions. That would be stupid. Minus. And this is also max with like 0, because if this is negative, it gives us more positions, and that's not possible. So now we either show that this is optimal or we fail system tests. What happens will be interesting. Not really sure what will happen, but it should be interesting no matter what. But yeah, that is essentially my solution. My solution is to first sort the array of prices, and then fill in the even positions first, and then only after that fill in all the odd positions in the order of the sorted array. So if everything's distinct, then this has to be optimal, because there are only that many possible positions we can have. So this immediately solves D1. The question is, does it solve D2? And I would guess that it does, but maybe there's some case that there was not in the pretest, but it was in the system tests. We got C, nice. And now we get a really good rank for some reason, because we were speedy on this. And yeah, that is my solution. I will think about this a bit more, I guess, right now, and we'll see if we can prove this. And also, there's only going to be one x. No, there can be two x's, actually. But there's only going to be one x where it's greater than the floor of n over 2, because otherwise we would have more than n elements, and that's not possible. So we're only basically thinking about one element and what it does to the rest of the array. So if we arrange this element in any other way, like for example, think about the solution where we say we have way too many 2's, and then we put all the 2's at the beginning, and then we just kind of solve for the rest, right? So we can put a 1 here, a 3 here, 1 here, 3 here, and whatever, right? But that's not so good. Because then we end up missing out on more than that. If we have 2 2's, then we automatically reduce our answer by 1. And by the time we cross the floor number 2 barrier, we're reducing the solution by basically we have half of the possible candidate numbers left. So it's n over 2 minus 1 over 2. That's how many we get. So if we think of this like functions, this is going to be this is always going to be, it's going to remove twice the number of numbers as twice the number of candidates as my solution. So that definitely doesn't work. It uses way, it's very bad. But is any other solution better? That is the question. My D1 should pass soon. Is any solution better? I don't think it would be. Well, I don't know. This would be the thing to fail system tests on. How could any solution be better? Basically weaving in the most common element to still try and make any other possible valid elements we can. Okay, well I don't have an exact proof. I don't think I'll be able to exactly prove it. But the proof would have to hinge on the fact that there's only one element we care about that's going to reduce the number of things we have. And specifically, this is the reduction it makes in my solution. And if there's some better solution that both still has this as the maximum possible and has fewer reductions from this one element, that will be what disproves my solution. Actually, no matter what happens, because of pigeonhole principle and stuff, this many elements have to be consecutive, I think. That was my phone. Okay, we got D1, sure. I think the idea would be this many elements have to be consecutive. And so if that's the case, then all of the consecutive elements are going to remove any candidate positions. So I think that would be the proof, because pigeonhole principle states some of these have to be consecutive, And if they're consecutive, then automatically they can't be candidate positions. So my solution will like minimize the amount of consecutive ones. And or no matter what, you can't do better than losing this amount because these are going to have to be consecutive, and the consecutive ones are going to cause this loss to happen. Okay, that's the idea. I don't know if it'll pass. We'll wait for system testing to prove me right or wrong. But now we can finish off with E. E is a fun one because I don't even have ideas for F, so that is not going to happen. But I can go over E. And what happens in that case? What do I mean, what happens in that case? It's the solution. Okay, here's the problem. You're given a number n. You want to put all divisors of n in a circle. So for example, let's say n is 6. Then the divisors are 2, 3, and 6. You exclude 1 because reasons. That's just part of the problem. And you want to put all these divisors in a circle. Then in one move, you can take 2 adjacent elements and replace them with their lowest common multiple. For example, 6. And you want to do the minimum number of possible moves such that no 2 adjacent elements are coprime, which is equivalent to saying the GCD of all adjacent elements, the greatest common divisor, must be greater than 1. So for example, the GCD of 2 and 3 is 1, so that's bad. But the GCD of 3 and 6 is 3, and the GCD of 2 and 6, again, they're in a circle, so we care about the endpoints. GCD of 2 and 6 is 1. If it wasn't a circle, it would be easier, but yeah, it would definitely be easier, actually. If it wasn't a circle, the answer would always be 0, so that's not interesting. But yeah, that's basically the idea. And then what? I think the answer is still always 0 or 1, though, for this problem. And here's the reason why. So we can order these elements in the circle any way we want, and we want to minimize this number of operations. So I'm just going to describe my construction without like going into how to get there, because it's like just a very messy train of thought. And well, okay. So first, let's represent a number as we can represent any number as the product of some prime powers. A prime power is some prime number p to the power of k. So it would be like p, etc. You know what a power is. And like p1 times k times p2 times k, or times p2 to the k, k1, k2 times p3 to the k3, etc. Right? Okay. Cool. It's a very messy thing. And the reason this works is because like either a number is prime or it's composite. And then if it's composite, it's a product of some primes. If it's composite, it has more than one divisor. And like, yeah, it just works. You can decompose a number into this. Like think about a number that can't be decomposed into prime powers. Then it's composite because otherwise it's prime. And then you can divide it into 2 numbers, both of which are composite, and you can just keep going until you get to a prime, or until you get to a bunch of primes, and then you'll just like get prime powers, you know? that will be how that works. So we'll consider the prime factorization. Let's take a specific example. The example I used while solving the problem was like 2 to the 7th times 3 to the 3, I think, times 5 to the 1 times 7 to the square times 13 or something. Or I think it was 5 to the square. Doesn't really matter what it is. Yeah, 5 to the square times 7 to the 1 times 13 to the square. Okay. So there's a well-known formula for counting the number of divisors given the prime factors. It's the product of ki plus 1. That is, it would be 8 times 7 plus 1 times 3 plus 1 times 2 plus 1 times 1 plus 1 times 2 plus 1. And this is the number of divisors. This includes 1, by the way. The reason being is that you can take any number that has you can take any number of these 2's. You can't take like 2 to the 8th, for example, but in any divisor, you can take 2 to the 0, or you can take 2 to the 1, or you can take 2 to the 2, or 3, or 4, or 5, or 6, or 7, you know? Because you can take any of those, and it's still going to be a divisor because it's divisible by n. It's divisible by a divisor of n, which means it's divisible by n. So you have 8 possibilities. You can take any number from 0 to 7 of these 2's. You have any number from 0 to 3 of these 3's, any number from 0 to 2 of these 5's, any number from 0 to 1 of these 7's, and any number from 0 to 2 of these 13's. So for this you have 8 possibilities. You have 4 here, 3 here, 2 here, and 3 here. So that's where this formula comes from. But we can also use it kind of constructively. And actually, this formula, if we exclude 1, then we have to subtract 1, because that's the equivalent of 2 to the 0 times 3 to the 0 times everything to the 0. Anyway, this formula is kind of irrelevant. So, what do we do? Let's focus on a specific prime factor. Let's say 7. Okay, now we have a bunch of divisors that don't include 7. For example, 7 to the 0. And then we can take the exact same divisors and we can multiply each of them by 7. 7 to the 1. There's a special case here. We can have 1 here. We can't have 1 here, but we can have it here. Because this would be like, that would be that. So that's a special case you should probably think about. Right? Okay. Now all of these numbers, all of the numbers in this range, automatically have the GCD of 7 to each other. So really, there are 3 things you have to be concerned about. This number with this number, the numbers at the 2 ends, the numbers on the circular ends, and the numbers in here. So let's say we found an optimal ordering for the numbers in here. Let's say, for example, we have like x1, x2, x3, x, I don't know, k something, right? Then what we want to happen is we want both of these to be divisible, or like to have a common divisor. So the best way we can do this is just to reverse this. Like x to the k, or xk x3, x2, x1. And this is very simple. And we can basically, like, we have a 1 that isn't in here, but is in here. Or it would be of the form 7. So we can just stick that, like, literally anywhere. What I did was I just put it after the first element. And this will work. If we have more groups, 7 squared, for example, then we can do the same construction, xk x1. And this works because automatically, any number in these 2 groups have a GCD of 7. Like this, both of these numbers are divisible by 7 because this is 7 to the 1, this is 7 to the 2. So we don't care about this barrier. All we care about are the barriers to the end. So we have two groups. Anything not divisible by 7 and everything else divisible by some power of 7. Okay, so now we have to find the optimal ordering for this group. And this is equivalent to saying, let's get rid of 7 and then solve for the rest of this number. So now we're solving for 2 to the 7th times 2 to the 7th times 3 to the 3 times 5 to the squared times 13 to the squared. And we just keep going. This is recursive. We make this like construction and then we solve recursively for the optimal value until we get to exactly one prime factor. For example, we have like 2 to the 5th. All right, then the numbers we have are 2, 4, 6, no, not 6, 8, 16, 32. And we can take any ordering of this because all of these are already coprime, or not coprime, so that works. So we're done once we get to one prime factor. That's our base case, essentially, of this weird recursion. Now, the only time where we actually ever get two elements that aren't coprime is the following situation. We have p1 to the power of 1 times p2 to the power of 1. That's it. And the reason being is, let's say we have like 2 times 3. Here we have 2, and then we have a barrier here and a barrier here. So no matter what we do, we have to put 6 somewhere and 3 somewhere. If we put 6 on this side, then this barrier is fine, but this barrier takes 1 combination. And here, this barrier is fine, but this barrier takes 1. The reason why it doesn't take more than 1 is because automatically, once we combine these two into their LCM, which is 6, we get 6 and 6, so we're done. So, with this construction, the number of elements, the number of operations we have to do to make the array valid without any coprime elements is, let's check this again. Oh, we got D2. Cool. So my proof was right, kind of, or my solution was right. Yeah. So the only time where we ever have to do an operation, like we'll be done after that operation. In this case, it's going to add exactly 1. If we have any other case, like for example, like if we have 1 prime, automatically we have 0 because it's just prime powers and everything is divisible by that prime. If we have more than 3, then we'll end up solving recursively, and we have more than 1 element in this range. So for example, these numbers are 2, 3, 6, and these numbers are, so we can construct it like 2, 3, 6, then 6 times 5, 30, and then we can put 5 in here arbitrarily, and then 15, and then 10. So these numbers match by 2, and these numbers match by 6, so it works. And note that this is the exact same construction we already have. We reverse it, we stick 7 right in here, or basically anywhere that isn't the first or the last element, and it just works. But it fails when we have exactly 1 prime, because we can't stick the 7 in the middle. It has to be on one of the ends, because we only have 1 other element. So that's the only time when it fails, and in that case, no matter what we have to take, we have to have like 1 coprime thing anyway. Yeah. So that's what happens there. Although actually the optimal ordering of this would be 2, 6, 3. And even here, even though we get to this case, because this isn't a circle anymore, like this still works. Because this isn't a circle anymore, like we only have to care about one of these boundaries. We don't have to be concerned about both this to this and like this to this. at the same time. We only care about one of them, so we can optimize specifically that one and not care about the other one. So that works great. And yeah, so I think the only case ever where we have like a single 1 is where we have this case, like p1 times p2, both to the power of 1. In any other case, we're always going to have 0 coprime elements because we can arrange the array in this way. Was there anything else I was talking about? I don't think so. So that's kind of why this is optimal. It's kind of a sketchy proof, but I think it works. We'll find out after system tests, I guess. And yeah, so this is the construction. This will like always work if you take the prime with the smallest number of occurrences. Although I don't think it actually matters. I think you can take any prime factor and then remove it and then solve for the rest, no matter what. Because no matter what, you won't end up in this case. This is only a problem when this is n. If it's not n, and there are some other prime factors that we're not considering, but we're solving for this like in the recursive version, it should still be fine because the only problem is the circle. Were it not a circle, we would automatically have 0 because all we have is one gap to worry about. Like we have, for example, this, and then we can put this down. But we don't care about this. So we can just put the multiple of 2 down here, and then we'll be done with this gap. And that makes it easy. Yeah, that is the... And it actually turns out to not even be an edge case, because automatically the construction will just handle this. And at the end, what I did was I just like literally checked the answer. I just counted the number of adjacent elements, possibly circular, that were coprime, and then that would be the answer. So you don't even have to do any casework to figure out the answer. You just literally compute it. So yeah. To recap, what I did was I chose the prime with the minimum number of occurrences, or the minimum prime power each step. Although I'm going to resubmit after and check if I don't even have to do this, if I can just take the first one. I want to see if that's a thing. And once you do that, then you break them up into groups like this, and then you recursively solve for the optimal ordering, excluding this number. And then once you get this optimal ordering, you reverse the ordering, and then automatically these two aren't going to be coprime, and these two aren't going to be coprime as long as you can stick the extra 7 you need in between 2 elements. So you need there to be at least 2 elements in this place. Otherwise, you would be slightly screwed. No, I'm wrong, actually. I was wrong earlier. A correction that it does matter, I think, if you have 2 times 3 times 5. Wait, no, it doesn't. No, this doesn't even do that. Okay, nice. Yeah, I don't know what I'm saying. I don't think it matters. Because my output for that test case was something like 5, 15, 3. And then this only fails if it's a circle. But because this isn't a circle, we can do this we can do the same strategy. And okay, so I was not wrong earlier. So, yeah. Correction to my correction. I was right. And you don't have to do any casework to figure out the actual number of adjacent coprime elements. You just you can compute it at the end based on the definition of the problem. So that is E. those are my solutions to all the problems I did solve. I did not solve F, so that part is sad, but I guess check out, I don't know, if Second Thread ends up solving it, you can check out his video, or others, other legends. And yeah. Where are we right now? Where are we in system testing? So I was looking at F. Any problem? We're at 48 minutes. Okay. I want to stay until my E system test just to like confirm or deny my own idea. Right now we had a great start on A, B, C, D, E. A lot of people failing A somehow. So this was D2. Oh wow, that guy failed A too. Although he'll probably beat me by having F. Yeah, he'll definitely beat me. How did that even happen though? That's a weird bug. I want to see what these people did. For I equals 1, I was listening equal to n. I guess equal to is the problem? I don't know. No, they're fine with that. Like s plus 1 something. I don't understand what's wrong with that actually. Why is this I plus plus? Oh, is that the issue? And somehow that passes pretests? S dot size equal to 1. Okay. So what happens here? Count I mod 2, C mod 2 plus plus. Okay, count last guy. Last guy XOR 1. Okay. Why is this reversed? That's a weird thing to do. Why is that reversed? Wait, what's the point of doing that? Is that the problem? I think both of these should be 2 and somehow this passes pretests. These pretests must be weak then. Like crazy weak. Yeah, this is I plus plus, which is the problem. Because it only depends on the odd or even positions, not both. This is I minus equal to 2 though. So I don't know what's with that. Maybe this is the problem. These should start from 0, because that's... No, it depends only on the parity of n. So I guess you could do casework like that. I don't know why that fails. Okay, where is status now? 3 minutes. In 3 minutes? Okay. So, this whole mess is my idea for E. Hopefully it works. Hopefully it passes. I don't see why it wouldn't, but maybe it won't. I don't know. Pretests for E, pretests for A were definitely weak, so maybe the other ones would be too. What is this solve order? Like A, D2, not even D1, and then C, and then all the way to F. Nice. Div 1 people are interesting, for sure. You just skip B. I went for C, D1. Okay, anyway. Just looking at random people. Just waiting around, kind of stalling. I just want my E to be judged. Okay, what's up next? There's a lot of stuff up next, actually. Tomorrow, Tomorrow I will be doing this contest, which is at 8 a.m. That's going to be fun. And I'll do a screencast for that, much like this one. After that, on Wednesday, because I have time, I'll do a stream of this contest that I missed, and also the chef. Go to this one. We'll do the cook-off, which I'm not going to do because of the @coder contest. I think that's more worth doing than this. So I'll virtual the beginner contest and then just like upsolve the cook-off after that. Then on Thursday, I can do solutions for this round. Then on Saturday, we'll have a special for this lunchtime. It'll be special. Very, very special. Very special. And Sunday, we'll do the, what is it? We'll do solutions for 673. And then after that, on Monday, I think I'll be free, so I can virtual this, and then whatever else comes up. I can register for this now. Not forget later. And yeah, that is the plan for the upcoming week. At some point, there may even be more stuff if more contests pop up, but there's going to be a lot coming soon. Should be exciting. How far are we now? 55 minutes, okay. This number of submissions should die down as people, like, more people solve A, B, C, the easier problems. Oh, it should be quick. Interesting. It's either running on test 1 or accept. Whoa. People FST'd D2. Is this some weird solution here? I don't know. How are the system test fails, actually? So we can check A and then reject it. And a lot of fails here. A lot of fails. How far does it go? 10. 15. Wow. 20. How far does it go? There's just this wall of people who've failed on these later tests of A somehow. A binary search on it. So 30 pages, which is like something like 1,500 people. That's crazy. What about B? Has anyone failed B? I imagine they wouldn't. I don't know how they would actually, because it's just kind of a formula. Runtime error, TLE. Okay. I don't know why that would happen. C is, whoa, more on that. We're gonna have some interesting timestamps for this video. How would you fail this one? Isn't it just the casework? Although I'm not sure. Okay, not that many, like 50 or so. Maybe my place will go up a bit if you do F. People FST multiple things, that is good for me, because then it drags them below me. Or just someone who even just solved E faster than me. What happens here? Okay. Has anyone failed? Running on test 1. Runtime errors. Weird, because I don't think it's possible to get wrong answer once you get the idea. Wrong answer on test 67. A lot of these. Wow, okay. E I don't want to check yet because I still have to judge for that. F I can look at that. I don't think many people would have. Oh wow, already. That was the guy in my room that got it. So he went backwards. Someone's already gotten it. I just want to know, man. I just want to know. Testing at 59, which means we have 8 more minutes to go. I don't really know why I'm waiting on the screencast. You can probably just skip this part. There's not going to be much substance here. But I kind of just want to do it, just to maybe make a comment if I do end up failing E. It doesn't look like many other people have failed E, so I'm not sure. What have other people done? Tried F. Got wrong answer. Other people also tried it. So this is a fail on 67. These pre-tests are amazing, aren't they? We're at 1 minute now. These system tests aren't the fastest because they have a lot of system tests, I think. Not many pre-tests, but a ton of system tests. We're at basically the top of people with ABCD1 or ABCD. That's cool. Close out paint. What else can I talk about? Someone's finally got an F. I think it's the guy that's currently first right now. Interesting. Neil is a monster. Just tears through these problems. Okay, we're at 101. Cool. We're answer on test 22. Interesting. By the way, even though it says rejected, these are accepted because it counts running as not passed, which I guess is a thing. How fast is this going? Is it going at a rate of a second per second, at least? Okay, it's at least a second per second. So we'll have 6 minutes until we finally get our solution judged. And then I can be done with this. Now 2 people, yeah, have FST'd. A, or many people actually, many people in my room. One guy's still waiting for judgment. Interesting. Where are we now? 103, okay. Watch my rank drop. If we end up failing E, we're gonna have a bad rank after all this. Yeah, this will not be good. Screencast of waiting around. What an interesting video, isn't it? I would love to watch this. This is kind of cool though. Usually the verdicts don't update like this. It just takes a while for them to update. So any sys test fails in this batch? Anything? We do get a wrong answer. Look at the next one. Bunch of accepteds. That one's boring. More accepteds. I guess B is testing quickly because there's not much to test. Why do they need 40? They have so many tests for B though. Why do they need that many? Like, isn't it just formula? Kind of. I'm not sure. Oh, rip D2 again. Another A fail. Ouch. $61. That was slow. This should be the period where there's like a lull in submission, so there shouldn't be that many. More accepteds. There were 15 pre-tests for E, I think. So we get past those, then it's the time. So the moment of truth right here. It's coming up. If we don't get this, we're in a bad spot. Where are we going to be 69th right now? We got it. Okay, that was satisfying. Alright, now we're in 22nd. That's going to be my peak. My rank's going to drop after that as more people get F, and I don't. Yeah, but that is the end of this. I just wanted to see if I got E, and I did. So that's awesome. I'll upload this as the rest of the system tests run, and I'll put my final rank in the title, description, whatever. Anyway, yeah, that's it. Okay, goodbye.